Good morning to everyone. Today in this video, this is your lecture number 8. So we are in the lecture number 7, we are discussing regarding the analysis of unsymmetrical faults. Okay. So analysis of unsymmetrical faults, there are 3 points which we have to remember. What are the unsymmetrical faults? Unsymmetrical faults are categorized as single line to ground fault, line to line fault, double line to ground fault. All these faults came under the category of unsymmetrical faults. So what we are doing the analysis of unsymmetrical fault. So we had taken the concept of, in lecture number 7, we had taken the concept of single line to ground fault. When we are doing the analysis of single line to ground fault, we have to calculate two important parameters. The first one being the fault current and the second one being the phase voltage. So in lecture number 7, we had concluded with the derivation of fault current. In today's lecture, we will derive the derivation for phase voltage. According to the derivation for the fault current, according to the expression which we had derived, we came across this circuit diagram. So this circuit diagram is showing how fault current is calculated. So from this circuit diagram, we can say that the fault current, that is current across the R phase, can be calculated by connecting three impedances, sequence impedances, named as positive sequence impedance, negative sequence impedance, and zero sequence impedance, in series with a generator of voltage 3 times the ER. Okay, so simply we can calculate fault current from this circuit. So the symmetrical component method makes the whole system very easy. It converts a three-phase system into a simple system comprising of three impedances in series with a generator having a voltage 3ER. So symmetrical component method makes our calculations very easy. Okay. So we had assumed in this key fault occurs across the R phase. So the nature of the fault is single line to ground fault. So while deriving this whole analysis, we had made few assumptions that I am just revising what we had done in the previous lecture so that it will give a sense what we are going to do today. So the first point is EMF generated will be of positive sequence only. The first assumption is when we have to derive something, we have to make some assumptions. The first assumption is EMF generated must be of positive sequence only. The second assumption is only the fault current flows other than the fault current will be zero. For the reference, third assumption is for the reference we had taken the R phase only, and the last assumption is the impedance of the fault is zero. By considering all these assumptions, we had started our derivation. So now start with the today's topic, that is to calculate phase voltages at fault. In the previous lecture, we had calculated fault current due to the fault. In this lecture, we are going to calculate phase voltage due to the fault. Now let us calculate the phase voltages at fault. Example, voltage between each line and fault. Since the generated EMF, since the generated EMF system is of positive sequence only, the sequence component of EMF in R phase are E0 equals to 0, E2 equals to 0, E1 equals to ER. Why this? Because while we are deriving the derivation, the assumption number one is the generated EMF will be of positive sequence only. So from that assumption, we can say that E1 must be equals to the ER EMF across the R phase, E2 equals to 0, and E0 equals to 0. The sequence voltages at the fault for R phase are, so we can say that V1 equals to ER minus I1 Z1. I1 we had already calculated in the previous derivation. Substitute this value of I1 in this format. So when we multiply the denominator by this and subtracting it from this equation, the final result which we will get in will be in this format. Okay. Similarly, we can calculate for V2. V2 equals to E2 V2 equals to E2 minus Z2 I2. So the value of EMF across the negative phase will be the 0. Similarly, we can calculate for V0. V0 equals to E0. V0 equals to E0 minus I0 Z0. The value of E0 again will be 0. We had substituted the value of I2 here. We have substituted the value of I0 here. All these values will be same. Only the normal subscript will be changed. V2 matlab Z2, I0 matlab Z0. So when we add on all these three equations, when we add on equation number 1, equation number 2, equation number 3, when we add on this equation with this equation, with this equation and this equation, we can say that the sum of all the voltages are equals to 0. This is expected because R phase is shorted to ground. अगर R phase short है ground में तो maximum current will flow across the R phase and there will be the minimum voltage. In ideal conditions we can say that the voltage is 0. So the phase voltages across R phase will be V0 plus V1 plus V2. Phase voltages across Y phase will be V0 plus A square V1, and phase voltages across B phase will be V0 A V1 plus A square V2, where A is the operator A. We had already discussed what is the useful use of this operator A. Operator A just shift the vector through an angle 120 degree in the anti-clockwise direction. We have discussed the functioning of A in detail in the previous videos. So this completes the derivation for the single line to ground fault unsymmetrical analysis. In the next derivation, we are going to discuss the double line fault, line to line fault, and in the further topics, we are going to discuss the double line to ground fault analysis. So from this whole picture, we had some conclusions with us. Those conclusions are, the first conclusion will be unsymmetrical fault. In unsymmetrical fault, positive sequence component, negative sequence component, and zero sequence component shows their presence. Whereas in symmetrical fault, only positive sequence component exists. There will be no zero sequence component or negative sequence component. अगर किसी भी सिस्टम में जीरो सीक्वेंस कंपोनेंट्स या नेगेटिव सीक्वेंस कंपोनेंट्स फॉर द करंट्स और वोल्टेजेस हमें शो होते हैं, तो वी कैन से दैट दैट सिस्टम इज द अनसिमेट्रिकल सिस्टम. अगर किसी भी सिस्टम में हमारे सिर्फ पॉजिटिव सीक्वेंस कंपोनेंट्स ही शो होते हैं, दैट सिस्टम इज कैटेगराइज एज द सिमेट्रिकल सिस्टम. So this whole method, symmetrical component method, makes our derivations very easy, so that we can do the analysis for the unsymmetrical faults. Why we are doing analysis? So that we can find out that during this fault, how much is the maximum current that flows across the circuit, and what will be the voltage between the phase and the fault. By calculating these two parameters, we can decide the rating of the switchgear equipments used. Okay, so this is all regarding the today's session. Thank you guys.